Good. So we should be recording now. So good morning again for the third lecture of natural language processing with deep learning. And as I said, like today we have a lot to cover, so let's get started right away, and we should make it on time. It's going to be a deep dive, this lecture, and I hope a little bit exciting. So finally, we're going to bring together everything we had the first lecture and in the second lecture somehow together and to try to build something actually which does something with text, right? So just to recap, we were talking about gradients and derivations last lecture, which was like the mathematical background which we will need, and we start talking about the computational graph. So we'll start from that and finally come to this backpropagation algorithm, which is very helpful for learning. And then we will deal with binary text classification. So finally, we can do something with text, some sort of machine learning with text. And we will cover one family of models, which is a kind of simple, but at the same time powerful family of models, so-called local linear models, and a few other things which are important for it. So let's get started. So let's start with this notion of computational graph. I think we touched this in last lecture already. So what is the computational graph? So basically you have a function which is composed of other different functions, and we had this example of x squared, sinus of x squared, which is composition of sinus function and x squared function. And you can express any sort of such a function in a graph, which is a directed acyclic graph, so DAG. Everybody heard DAG before, acyclic graph? Graphs like nodes and edges and stuff like that, right? Okay, cool. So each node of this graph is some function. So here we have f2, f3, a, b, and things like that, which has some arguments. So the arguments of function f are a and b, and the leaves of this graph, it can be actually a tree, but doesn't have to be a tree necessarily. It could be like, there could be some sort of like diamond shapes in the graph as well, but as long as there's no cycles, we're good. And the leaves are some sort of variables, which is the input, and the arrows are function composition. Okay, doesn't make sense? You can compose a function, so whatever, you can try. What could be the sinus of x squared? Could be, we have x, it goes to something squared, and it goes to something sinus, right? This would be the graph. Any questions? Good. So in general, we can have each node in the graph can have multiple, and now the question is like, what is a parent and what is a child? So it's depending like how you look at a tree. So sometimes you have children below in the tree and parents up in the tree. Sometimes it's up to you. So, I would say these would be the children because they're coming into the node, and these would be the parents because why not? But it might be the other way around. It's up to you to say what is a child and parent in a graph. But these have like multiple, let's say, arguments and multiple, I would say, like consuming nodes, which are used, which using this output of this middle function. Okay, so this is some generic node in a graph. Okay. The most important part for this to work for our purposes is that each of those have to be differentiable. So it has to have a derivative. Why do we want all those functions to be differentiable? Why do you think we need to be differentiable? Any idea? Any idea? You? Any idea?
To be able to get the gradient?
Oh, exactly. Yeah, we're looking for the gradient. Okay, good. So everything needs to be differentiable because we're looking for the gradient. Why are we looking for the gradient again?
To be able to backpropagate?
No, backpropagate is a thing to get the gradient, I would say. But why we need the gradient in the first place?
So we can know how much each neuron contribute in the loss function?
How much each neuron contributes to the loss function is basically the output of the neuron. Like the output is, the end of that graph is the loss function, and how much each neuron contributes is like how much they produce. So this is not what we need the gradient for. Any other ideas? You have one idea?
We want to minimize our loss, meaning...
Yes, right. We want to minimize the loss. So, and how do we minimize a function?
derivative and then solve it for 0?
No, we don't solve it for 0. I mean,
in this case not, but
yes.
We just need the direction where we need to go.
So the gradient is the direction. Yeah. What is it good for then? What do we use it for?
We need the direction where we find, in optimal case, the global minimum, but we need to find where the local minimum is and in which direction the gradient has to walk after each iteration.
So the gradient doesn't walk, but the gradient gives us a direction of something. What is?
We have steps for it.
Yes, we make a step, but what is the gradient telling us?
In which direction we need to move.
I don't think so. I mean, it's somehow, but it tells us something different. Yes? Yeah, we're updating the parameters, but the gradient is telling you like something. I mean, it's telling you a direction, but there's a little tiny detail. The gradient is consistent of partial derivatives with respect to each dimension, basically, sure. Yeah, but this is telling you like where is it growing. That's the point. The gradient is telling you the slope, and the slope is positive because the function is growing there, but you need to go the other direction. So you were right, but there's this tiny little detail you need to subtract the thing. You know, does it make sense? I mean, if you follow the gradient, you'll end up in the mountains somewhere. So you need to take the opposite step. But everybody was partially right and partially like with a tiny little detail wrong. Does it make sense? Okay, fair enough. Cool. So this is the gradient. So this is why we need like all these kind of functions to have derivatives, because we want to minimize the loss. This is the whole story. Okay. Now, how do we do it efficiently on computational graphs? Because computational graphs will give us some very nice properties to do so for very complicated functions. I mean, you can do the partial derivatives like per hand. Take a function and then do like partial derivative of loss with respect to parameter 1, parameter 2. Sometimes it's possible, most of the time, like not really. You don't want to do this. So backpropagation is the algorithm not to train neural networks. Backpropagation is the algorithm for efficiently computing the gradient. You can do computation of gradient in many different ways. Backpropagation, one of those, which is like super efficient for reasons, but you can do it per hand. If you have the gradient, then you can minimize your function and do it like the gradient descent and stuff like that. But backpropagation is just for computing gradients. You can do it for, computing gradients. You can do it, whatever you use it for, it's up to you. But it's used for training neural networks. So let's do a working example here, which is a very, I would say like very simple function. So, so we have a function consisting of a plus b times b plus 1. And these are our sort of input parameters. And we want to compute the gradient with respect to a and b. So how many dimensions the gradient will have? Yes? 2, yeah, 2 parameters, 2 side gradient. So what we need to do is, what is this? How is it called?
Nabla.
It's called nabla, exactly. This is the gradient. We need a partial derivative of e, which is the output, and with respect to a, and we need a partial derivative of e with respect to b. So this is the gradient, but I mean, this will be some numbers basically. It's going to be a vector showing us like, oh, this direction is the opposite of going to the minimum. So we need to compute it for some numbers, but I mean, we want like the derivative computing function. So whenever we are of a and b, we need to get the value of the gradient. So this is the whole idea. Like it should be generic, gradient computing function. All good so far? Any questions? Okay, so can you do the gradient of this function per hand? Yes, exactly. It's very simple, but that's not the point. Like we need to use the computational graph. We want to use the computational graph as a working example here. All right. Good. So let's take this function and add some intermediate names of nodes, and add some function more that so everything is super clear. Because in functions, like if you write a function, there's this function definition, which is this f, and there is this value, which is the output of the function. And sometimes you can use the name of the function as the name of the output. Sometimes you want to have a variable for the output, and sometimes it's just super messy. So in this case, I was very explicit and put like f1, f2, f3 are functions, so with the f, letter, and E, R, S, and whatever are the variables which take the value of the output of the function. Okay, so just to be very explicit and sort of rigid here. Good. So how do we build a graph here? Yeah, I mean, if I ask you how to build a graph, you have to draw it. So let me just show it. How we build a graph, but it shouldn't be surprising right now. So as we said, each node is a function. Okay, so we start with the leaves, which is A and B. So these are the input parameters. So like A, B. So there's no other variables coming in. Okay, so there is this function f2 taking A and B. So this is a A plus B is sort of this node, and there's another node which is the B plus 1, which is this node. What we can also do is to add 1 here and add one extra node with 1, but it kind of makes no sense. So let's call this node just it's a plus 1. So this is a sum node, and this is like plus 1 node. That makes sense? Okay, cool. And now the last function here is just taking the product of R and S. So this is it, and let's call it the product node. Very simple. So now, I mean, you can now, how would you compute like the value of this function for n, A, and B? How would you compute this? I mean, you can implement this as a graph in a whatever Python and something. How do you compute the value of this function for A and B? Yeah.
Plug in the values.
You just plug in the values and see. Yeah, but how do you see what the output is? I mean, how do you compute the output? That's a question. Like, how do you compute the output on this graph?
Like, for example, here, if we know A and B, we can just say R is A plus B and S is B plus 1, and then for E it is B.
Okay, so what you're describing now is you're walking through the graph on the path and waiting for each node for its arguments kind of to evaluate, and then you can evaluate a function. For evaluating R, you know A and B, so we can evaluate this. But for E, you need to evaluate also this node. So you can do like recursion. So you start at the output and calling all the children. Oh, I'm calling this children. Calling all the children, oh, give me your output. And then you collect the output, and you recurse the graph until the bottom, and you can trace back to get the function. Makes sense, right? I mean, this is one way to compute. The other way could be I'll just start from the bottom, and whatever comes next as a parent, I'll just plug in the values and compute. So one is sort of backtracking, recursive computation. The other is like, I think they call it like forward pass. So you start at the beginning and you forward it to the end. Okay, so this is how you compute the output of this function. Any questions? Okay, cool. I mean, this is somehow common sense. I mean, you would figure this out. If you had to program this, you would figure out how to compute this, because this is the easiest solution. Okay, so now our goal is to compute, as we just said before, the gradient. So these two partial derivatives of E with respect to A and B. So how are we going to do this? We're going to compute the derivative for every node. So the sort of partial derivative of the output. So the output is the E function with respect to every node. This is what you're going to compute. If you compute it for every node, then we're going to compute it for this node, but also for this node and this node, which is the gradient we are looking for. And by doing this for every node, we'll figure out, oh, there's actually a nice little trick that kind of helps us to do it very efficiently. Okay, so this is the goal, how to compute the gradient for every node. So where do we start? We start at at the output value at the top. And now the tricky part is like, what is the partial derivative of E with respect to E? The answer is 1. And why? I mean, sure. Just what is a derivative? It's like the rate of change. So if you change E by something, how much E changes? Well, 1, and the ratio is always 1, okay? So this is the only sort of hard-coded thing you need to plug into your computational graph. So this is how you start with the partial derivative of output E with respect to itself is 1. Good. So now, in this function, I mean, it has to be differentiable. So f1 has to be differentiable with respect to its parameters. So now we have to ask, what is the partial derivative of this function with respect to both arguments, so to R and S? So we are interested now what is partial derivative of partial derivative of, I'm going to call it E. So what is a partial derivative of E with respect to R and what is the partial derivative of e with respect to the other argument, s. So we need to do it for every argument. Good, so the question is now, what is the partial derivative of e with respect to r? So this f1 function is this one. So what is the partial derivative of this function with respect to r? Ooh, okay. So this is the homework, like partial derivatives. You need to refresh this very well. What is the partial, again, what is the so if you do partial derivatives of one variable, you take the other as a constant. So what is the partial derivative of r times s with respect to r, yes? S, exactly. It's s. So now you may guess what is the partial derivative of this function with respect to r. Oh, sorry, s, with respect to s, sorry. Which is r, exactly. Product. Okay, so refresher, okay? Do some homework on partial derivatives. Excellent, so we have this, nice. So now we know how to compute these partial derivatives. So let's move on one slide. So this is exactly, I'm gonna call them, it's not a convention, but we're gonna call them local partial derivatives because they are somehow local to this one function with respect to arguments. So this is, sort of like internal, we call them internally, and we call this global internally because this is like output with respect to the node output. So, and sanity check, I mean, R and S are some concrete numbers, so of course then these partial derivatives will be some concrete numbers. Once you plug in A and B, you will compute the output of the function, which is number E, and then, because you know R, then you will know what is the partial derivative, or you know R and S, you will know exactly the value of partial derivative of E with respect to S. It will be a number. So basically these are like tiny little variables or formulas, but these will be numbers at the end of the day. Like the values will be numbers going forward, and then the partial derivatives will be numbers computed for each node. That make sense? Any question? We're good now. Okay. So what we're gonna do next? What do you think? We're kind of, going from the top. Oh, remember. We're going from the top to the bottom. So what are we going to compute next? Any idea? What do you think?
Partial derivative of r with respect to a and b, and the same for s.
We're gonna compute a partial derivative with respect to a and b. Yeah, we can do that. Sure. Another option. That's a good option. Another option. What can we compute next? So we started in bottom, and we have this global derivative here with respect to this node. We have the partial derivatives. What can we also compute now? Yeah.
The partial derivative of those derivatives?
Which was derivative?
I mean, we have e to r, so we now can take r to
A. That's what you said. You would go to the next child. Okay, so let's move here. And what can we compute here in this child? Sorry, child like this, or A or B? I mean, okay, so the idea is like what we said. Let's come back. We want to get partial derivative of E with respect to something for every node. So we started with partial derivative of E with respect to itself here. And what we want is the partial derivative of E with respect to R in this node. Like this global thing here, partial derivative of E with respect to R, and here we need a partial derivative of E with respect to S. That's also an option. So we can compute this because it will be helpful to computing something else down the road. Yes?
So the goal is to compute the partial derivative of e with respect to a and b.
Exactly. This is the goal. Because why? Because this is the gradient. This is what we need. We need to compute these partial derivatives here down the road. And we're going to do this by computing this sort of partial derivatives for every node, because then we're going to use the chain rule sort of to get, at the bottom. But we're going like iteratively. So first we compute this global derivative, and then we, get these partial derivatives, because now we're interested in this partial derivative of E with respect to R. So let me just, sorry, this looks very ugly. So now we're going to say, what is the partial derivative of E with respect to R? So how do we get this? How do we get this sort of global partial derivative? I mentioned the chain rule. So these are composite functions. I mean, this function is part of this function. So how do you get a derivative of composite function? Yes.
Didn't we calculate partial derivative of e with respect to r?
Yes, yes, we did. So we can use it right away. Exactly. So now we have it already. Yeah, so it doesn't reveal the rule, but down the road it will reveal some different rules. So now we have it. Okay, good. Let's take it for granted. But typically, if we are somewhere deeper in the graph, this would be taking this local partial derivatives and multiplying by the upper function because of the chain rule. Like you have composite functions, you take the derivative of the outer function at the value of the inner function times the derivative of the inner function. So you're multiplying sort of two partial derivatives things. Okay, so this will be revealed later on. So for this node, it's pretty easy. So we need this sort of, I call it the global output with respect to the output of this node, which is in this case multiplying partial derivative e with respect to e, which is the parent global output times the local derivatives with respect to this child. So now this kind of reveals a pattern, because what is going to be the partial derivative of e with respect to s? It's going to be the same thing. So we take the global of the parent of e with respect to e times partial derivative of e with respect to s. So basically this times this, which is a chain rule. So it's basically the chain rule, but shown differently on the graph. Any questions? Does it make sense? Okay, excellent. So now, yeah, we're good. So now what are we gonna do next? We computed everything for these three nodes already, so we step down. So let's pick A. Okay, so what we are interested now is the children, we need this local derivatives here of r with respect to its children, so with respect to A, and r with respect to B. Okay, so let's compute those. So let me finish this. We compute this for S, but now we're going to compute these two things. We need these two local partial derivatives to respect to their arguments. So what is going to be, no, I'm gonna show this, sorry. The slide showed the answer. So what is the partial derivative of this function with respect to A? So this function was A plus B. So what is the partial derivative of this function with respect to A? 1. Okay. Because you take A and it's, you just do the derivatives, the rest is constant, so 0. Okay, what is the partial derivative of R with respect to B? Yeah, everybody's screaming 1, of course, yes. Yeah, the same, sure. Okay, so we have those. Oh, excellent. So now we have the local derivatives, which I'm showing them here. This is super easy. And now, again, now we're interested in what is the partial derivative of E, so the global sort of thing, E with respect to A. And now we just plug in the chain rule again. So what do you think we're gonna, multiply together now? You have an idea? Partial derivative of E with respect to, yeah, but you have to look just to the parent.
Okay, so if we just start from there, then it would be partial derivative of e with respect to r.
Yes.
Multiplied by partial derivative of r with respect to a.
Yeah, exactly. This is it, like this times this. Yeah. And now, if you think about, we said like it's not a fraction, but now if you just close your eyes and say it's a fraction, you get the answer, right? But chain rule is it's not a fraction. So you're just multiplying two derivatives. So you take the global derivative of the parent and multiply by the local derivative for this particular child. So seems good now? Now we know. Now we see the pattern, like why this would work also for this case, for this multiplication. This times this will give us, the global partial derivative here. So just take the output of the derivative of the parent. Okay, so this is good. We are here, so let me just show this in a very nice way. So we computed this again, the chain rule basically. This times this. Now, how about b? So what is still left? Okay, now we need to compute the partial derivative of s with respect to its parents, which is its children, which is b. Okay, so f3. So what is the partial derivative of this function with respect to b? Everybody screaming. 1. Yes. Good. That was easy. But thanks. Okay. Yeah, that's easy. So we have this. And now, okay, now we need to do partial derivative of e, so the global thing, so the global function, with respect to b. Yeah, but the issue is here, we have 2 parents. Here was easy. We just multiply the parent and the sort of the local derivatives together, and that's a chain rule. This is good. But now we have 2 parents. So what can we do now? What can we do? If you have a function and it has sort of like goes there and to 1, like 2 parents sort of thing, how do you do the derivative? There is some, you have an idea?
I think we should add those derivatives, but I'm not sure.
We should sum them up. So this is your motivation, which seems to be correct. And there's a thing, why can you do this, which is the generalized chain rule for multiple parents. We had this in the last lecture, so you want to refresh this. If you have multiple parents, you take the derivative with respect to, I'm just going to show you the result, and you will understand why is it so. That this is so, and there's a reason. The reason for this is the multivariable chain rule. So what we're going to do here is that for each parent of this node, again, we're going to take it's like global derivative multiplied by the local derivative and add it with the second parent node times the local derivative here. Okay, if we had 3 nodes, we would be adding 3 together. Here we had just 1 node, so summation is of just one element. Okay. Any questions? Good. What we just did? Yeah, we did what we want. We computed the gradient. We have here the way to compute the partial derivative with respect of the function, which is this function, this node, with respect to all its arguments. So it's somewhere like nested functions. There's some whatever, some path, some diamond path here. Here we see the diamond, right? This is the diamond. B is going here and through 2 paths. And now we were able to compute somehow, or have a sort of like algorithm to compute its partial derivatives. Because why? A and B are values, okay? Real numbers, 1 or 2, I don't know, something. So then we can compute the value of R, the value of S, and the value of E. So we have all these outputs. Good. Then we know this derivative is 1. We know how to compute this partial derivative, because this was again partial derivative RS is S. Yeah, but we have the value of S here. We computed it here. So we can plug it in. So this is a number, which means this will be a number too. We can multiply 1 by S to get this. Okay, nice. And then this is going to be also, this was 1. So now we can compute this number times 1 to get this, to get some number here. So basically we're doing computations on the graph. First pass through it, it's like to compute the output value, and basically tracing back all these local and global gradients will give us how to compute the actual value of the gradient for some values A and B. So the forward pass computes the values, and the backward pass computes the sort of partial derivatives of each nodes. Does it make sense? Yeah, it's somehow cool, right? You don't have to do it per hand. You have an algorithm which is doing it for you. And this algorithm is called backpropagation. So this is backpropagation because you're back-propagating the error. And the error means like, yeah, this is error if this were a loss function is telling you how big your error is, and you're propagating the error through the gradients back to these variables, because each of these variables, A and B, somehow contributed to the error because they were wrong. If they were right, like your loss is 0, so there is no error. But each of those have contributed to some, with some error, and you say like, oh, how much this error actually, will be from each of these elements to show, oh, I need to change it somewhere else, like to update the parameters, so to say, to make this error smaller. This is backpropagation. Okay, so this is I would say, spend some time on that, tinkering and trying out. We will have the exercise to actually program this and other things. And backpropagation is the only algorithm, there's a couple of other algorithms, but this is a core of any machine learning, deep learning and any training, is how to compute gradients efficiently. So we're gonna spend some time on that. We're gonna actually build a neural network from scratch by computational graph. We're gonna learn this, like how to actually compute these things in pure Python, no library. So you will understand very exactly what the heck is it doing. This is the idea, like the core of deep learning. Yes.
I have a question.
Yes, sure.
We find how valuable are variables A and B, but will we in the future also update functions like R and S, intermediate functions, or we will update on this inputs?
Yeah, so you're asking whether we will change something in R and S. Yeah, but R and S are not numbers, these are functions. Functions have parameters. You can change your parameters, but functions are a thing, like they do some operation. So there is, what do you want to change on this function?
+1, for example.
Yeah, so no, you're not changing your functions in the graph by learning. Not really, that's not the case. You define your functions, you have a set of functions which you're kind of fine with, you build your graph, and the only thing you care of, like how to find the best parameters to minimize your loss. So now, like how this, so this is again the generic node in computational graph, and we're assuming the graph is a function. So for each, we're taking, so here again, so we have the f. So this is the generalized chain rule for all the parents here. So f has the parents h1, h2, and so on. So we take, for each of those parents, we take their, which I call the global derivative, and compute by this local derivative and sum them up for all the parents. And then for each of the children, we need to compute the partial derivative with respect to each of those, children or parameters of the function or variables, input variables of the function. So this is the generic thing. So what do you think now if you're gonna implement a computational graph? So what do you need, what is the minimum set of things you need to implement for each node? So each node is a function, so it needs to implement something. You need to implement very few things. Let's say you need to implement x squared function. It's gonna be a node here. So what do you need to know? What do you need to implement for this function? Yes. So you need to implement the derivative. So derivative with respect to its inputs, arguments with respect to arguments. What else? Okay, I get it. This is important for the backpropagation to work, but what else you need to compute as well? I mean, it's very simple. Excuse me. Say again, sorry. You need to implement the value, yes, the output. Yeah, and that's it. This is the only things you need to implement for every function in your graph. And if you plug them together, your backpropagation will work. I mean, I need to implement the backpropagation algorithm going through the nodes and stuff like that. But as long as each node knows how to compute the output value and knows how to compute the partial derivative, then you should be good to go. Because the rest is kind of somehow global, in the algorithm of backpropagation. You will call these functions for each node, but then, the traversing the graph will be somewhere like, external to these nodes, sort of. Okay, so backpropagation is two parts. We made them already. So one is the forward computation. So we need to compute all nodes' output. How we do this, I would say the recursion. You call it on the last node, and it will call its children, and you will gather all this information, for example. And here's one thing. Cache it. What does it mean? What do you think like caching the value means? Yeah.
Saving it in like maybe something like a dictionary.
So we're gonna save it somewhere. Why do you think we should save it? Yeah.
Because if we will be recursing through the computational graph at each point, maybe we would need also values from others that could be able to happen.
That's right, because we might be actually using the values over and over and over and over, which means you don't want to compute the same thing over and over, so you better cache it. And actually, this is what makes backpropagation actually work. It's like caching the intermediate values. So what you want to do is cache, store somewhere values of A and B. Okay, I mean, these are constant, so you have them. But then store the values of R and S. Why? Because here, for example, for this gradient, for this partial derivative, you're calling the value of S. So now imagine you're computing this and you go, oh, what is the value of S? I have to look here, oh, the value of S is some function, I need to compute it again, blah, 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 so it's kind of boring. I mean, you need to compute it over and over, so you better store it, cache it, and then you just reuse it again. So it will save time. I mean, this is a tiny little graph, so it won't make any difference, basically. But later on, with, let's call it deeper graphs, so now we're getting to the lingo of neural networks, like deeper neural networks, because this could be a neural network. Like these are like layers, maybe a neural network, but it's a deep graph basically. It will make a difference between day and night. And I think we have an exercise to show this difference, like some deeper network. Like if you don't cache it, it will take 2 minutes to compute versus like 20 milliseconds or something. Okay, so this is the caching. So this is the only thing we need to compute for the output. And again, for the backward computation, so the backpropagation, compute the overall function's partial derivative with respect to each node, and again cache it, because we're gonna use it again. And what's the biggest issue with cache? I mean, in computer science, like what happens with? Say again? Memory. Okay, so if you're caching things, you need to have bigger memory. Sure. So how big the memory you need? Like the number of nodes, basically. But anything, even more like pragmatic, like what is the problem with the cache in general? If you cache something in your computer system, like what you're risking? The memory, yeah, you can run out of the memory, but it's even more or less something pragmatic, yes. Yeah, exactly. You just forget to purge the cache. You just forget to delete a cache, or it will be like sort of outdated cache. Like you store intermediate results and then you forget to clean them somehow by a bug in the code. Basically, you forgot to clean the cache, and then in the next iteration, it's like, yeah, but I'm getting like weird results here. What is going on? Like, is my algorithm wrong? And then okay, I forgot to clean the cache. This happens. So if we're gonna develop the thing from scratch with the cache, you need to be aware of that. Oh, I'm storing intermediate results. So maybe after this forward and backward computation, when I finally get what I needed, let me clean the cache. Because for the next iteration, if I move these somehow differently, A and B will be different, then all these computations will be different. So then I need to compute this whole thing again. But for one forward and backward pass, I'll have this cache. Yes?
Do we purge all the cache, or do we look which are affected by parameter change?
I think if you look into what is affected by the parameter change, you're just wasting resources. So you just clean all and run again. Yeah, because you need to have the memory for that already in the first place. And then like zeroing the memory, and basically you don't have to do anything with the memory. You're just saying like, yeah, I don't know, like cache invalidated flag, and then you're good. You're just writing in there. Okay, any questions? Does it make sense? To some extent, good. I mean, how's it saying? Like the proof of the pudding is in the eating. So once we start to implement this thing, then we will understand what it really means. But as a theory, yeah, it's kind of nice algorithm. Good. Okay, so now recap of backpropagation. So we can express any arbitrarily complicated function. This is really interesting. So we can really express any complicated function from, well, now we are limiting ourselves to, okay, so input is some vector, cool. because we know we can turn everything into a vector somehow. And we're saying this is going to just a one single real number. Yeah, sure, because you're optimizing just the loss. You're minimizing loss, and loss, what is a loss values? What loss can take on values? Any idea? What loss could be? Some real numbers, but what do you think? Like, is it, what properties loss has? Yeah. So loss is taking some values. So what these values are? I mean, we're saying this is a real number, but maybe it's not all the real numbers. Yeah, but it's not a real number. So loss is a real number, but what sort of real number is that? Yeah. Yeah, I'm asking. Okay. Basically, these are just okay. So I'm asking wrong question.
It's positive.
It's positive. Yeah, that was the wrong question I asked, but you would figure out. It's positive. These are just positive real numbers. It's a loss, and the smaller the loss, closer to 0, then we are matching, the labels with the predictions. Yeah, that's the whole idea. But it's just positive numbers, and this is the only thing. So any function which is any vector to real number, we can build as a computational graph, which is output something, and then we can actually compute efficiently the gradient of this function for a concrete point of this vector by running the forward pass and backprop. And the caching help us to avoid repeating computations. And that makes it a very efficient algorithm. Backprop, your new friend for training ChatGPT. This is it. This is the algorithm. I mean, the graph will be, I would say, like, a little bit bigger than this for ChatGPT, I would say. Like billion times bigger, but, it's still a graph in a way. And remember, like, the graph is just a way of how we represent the thing in our head, maybe, or the design. I mean, eventually it could be an array of matrices or array of vectors, and as long as you know what is the parent and the child, the implementation, actually, you can do it in many different ways. But the graph thing, at least me, helps to understand, like, oh, I can plug one more function here and one more there, and nothing will change because the algorithm will work. Because what you see usually, like, oh, let's build a deep neural network from scratch, on YouTube videos, and then starting already, oh, now we have the layer 1, layer 2, and this is how you do the backpropagation. Yeah, sure, for this one particular case, but this is so generic that you can build anything you want. You can have all these diamond shapes, paths, going functions as you will, while some sort of like just a multi-layer perceptron, which we'll discuss later, is a simplified version, which you can make more efficient if you implement it like for one case, but this is just generic sort of thing. Computational graph is generic. Good. So let's move on. Are there any immediate questions to backprop? So yes?
In the cache point, do we update the cache every time we make a backpropagation?
Yes.
With a new value?
Yes. Every time, I mean, because this is storing like the outputs of the nodes and the gradient, the partial derivatives. So, and they will change each time you change the input. I mean, you change the input to the function, everything in the middle will change. So you'll just purge it and run again. Yes. Any other questions? Okay, so let's move to test classification. Let me see if we make it to the end, but I hope so. Let's see. We're not in a rush, actually. Like, we can, whatever. Wherever we stop, then we'll continue. Okay, text classification. Interesting. So now we need to, bring these two words together, like this backprop and derivatives, blah blah blah. And what do I need to achieve actually? What I'm interested in. So okay, what are we going to achieve? So we have an example task, which is the binary sentiment classification into positive and negative. So tell me a data set which we can use for doing this. The IMDb data set, like the movies sentiment review data set, like the movies. Yes. Okay, so this is the task. For example, the IMDb data set or any other. And we will learn a simple, but like a little bit powerful, supervised machine learning model. So now you know what is supervised machine learning. We have the features, the input, and the labels. So this is supervised. Machine learning model, which is known as a logistic regression or maximum entropy classifier. But in fact, what we're going to do is a single layer sort of neural network. So this is like an essential and important building block of any deep net. So we're going to build this model. Okay, so yeah, now how do we plug these two together? So we have this text again, and we're now the whole math, like the gradients and functions and whatever. So how, I mean, obviously we need to represent our task, which is this sentiment classification, as a function. Oh, by the way, but we discussed this last time. We said like, oh, you can turn a classification problem into a function, and then you do with something with a function to learn this task. Okay, so we're gonna find a function which kind of maps, because a function is a map, which maps the input, which is the input text, into the output, which is positive or negative. This is the function we want to build. We need to turn it now into some mathematical lingo, and to, function is a mathematical thing, like how these computations actually work. So what are we going to do? So one example, very simple one, is linear functions. So linear function, as you might have heard, it's like linear function is a very simple function. So you take a line and project it into another line, sort of. So everything which is a line in one space is the line in the other space. So let's start with something more abstract and go to something even more simpler. So high-dimensional linear functions has some in number of dimensions and out number of dimensions. Okay, so let's say, okay, I'll give you an example. So let's say I wanna take a picture of this bottle in 3D. So what sort of function is that? Like what from which space to which space is it going? Or I'm gonna draw it. Okay, I'm gonna draw a bottle. Yes? Yeah, it's 3D to 2D, like 3D world, which we know. I believe we live in a 3D world. At least that's what we perceive. To 2D world, which is a space. So we're just doing like drawing. And of course, if I'm gonna draw it correctly, like a line on this bottle will be a line on the paper. Okay, this is linear projection, and you know it from computer vision, or not computer vision, like computer graphics. How do you project things into, like, how all the computer games, 3D shooters and things like how they work? I mean, there's some linear projections. How do you project a 3D object onto 2D object or 2D space? Yeah, by multiplying by matrix. Like there's some matrices which you take a thing, multiply by matrix, and project it to some other space. Yeah, okay, so this is it. So here we are given some inputs and some projection matrix, W, and this is we call it a bias. And you project the input thing to some other, from some dimensions to other dimensions. So it could be from 3D to 2D, could be from 64 dimensions to 64 dimensions, or I don't know how many dimensions you want to fit in. That's it. Like a generic form is like you have these input features, and then the matrix, you multiply by matrix, and you project it to somewhere else, and you can add some bias, which just tells you if this were 0, if the input is 0, the output will be just the sort of the bias term. Sometimes you can even like ignore the bias and just do the projection, which means you will keep the center of origin of that. So the projection will be around the center. So you don't move the center of origin. Sorry, what's it called? The origins. Yeah, you don't move the origins basically. If you add a bias, you're also like moving in the space. Okay, the question is like, do you have the mental model of this projection or not yet? Because this is an important thing. Like you need to understand what a matrix is doing. If I take a vector and multiply by matrix, I'm just doing linear projection, nothing else. So linear projection means all the linear dependencies between points in one space. So this is a line. It's like a linear dependency, sort of. If I project it by multiplying by matrix, it will be a line or a dot, but it can't be a curve. Its linear projection is like lines will be lines. This is the mental model I'm keeping in my head. Like, yeah, I'm gonna project it. I can like squish it, or squeeze it, whatever, but lines will be lines. If I want to turn it into something which is not lines, I need to use something else. But the linear projection is a linear projection. Vector by matrix multiplication. By the way, we're using here this notation, as I said, like we're multiplying vectors by matrices. Sometimes you see like matrix by a vector. But since we're using the row vectors, so this will be a vector, let's say 1, 2, 3, multiplied by 2, 6, 8. which will give you not a number. What will be the dimension of the output here?
Scalar?
It will be a scalar or just one number. Okay, so you need to refresh like how to multiply the bloody thing. That's just like partial derivatives is the math you need, and how to multiply matrices or vectors. This is what you need. But by the way, I think I have some appendix here in this lecture, so there's some refresher if you need to like really dig deeper into multiplying vectors and matrices. Okay, so this is it. I mean, so the vector x is the input, the matrix w and vector b are the parameters, and we use this very fancy theta thing for all those. So these are the parameters. And my function is x times w plus some bias. I can make it even more simple and just project. I mean, something which we did here actually is to project into a single number. Okay, sorry, just here. The goal of learning is obviously to find these parameters such that the function behaves as intended on a collection of input values and the output. So we need to minimize the loss, basically. This is what we know already. So we need to find these parameters that kind of somewhere there will be a loss, and we want to minimize this loss. But we want to do this by finding the best parameters of this linear function. We're going to make it even simple, and the output of this function will be just a real number. So here we have the input is let's say 1, 2, 3, and we're going to multiply it by. So this is now a vector 4, 5, 6, which is a very nasty multiplication. So it's just like a dot product, but maybe it's better to think about it. Oh, it's actually a matrix of size. Sorry, with one column. Like that, which gives you some single number, single scalar, n plus b. This is actually the easiest thing. So you have multiple input features, but you map it to one number. So far, so good? Okay. Excuse me. So now we have a function. This is actually, we're getting somewhere. We have a function which has some vector input, and it has some real number output. And it's almost like matching the case where we need to do binary text classification, because our input, well, not yet. We have some issues to solve first. Because our input is natural language text. It's not a vector yet. It's a text. It's a review of a movie. Like, how the hell I turn this into a vector? So this is the first problem we need to solve. And also, we have the labels, but remember, these labels are two categories, like positive and negative. So how do we turn this into a real number? Two things we need to solve first, but then the function kind of is okay. Maybe maybe it's like good enough expressiveness to solve this problem if we learn good parameters. So let's start with the simple one. So how we turn our labels into real number? What do you think? Yes? Negative 0 and positive 1. Okay. 0 and 1. Another option?
We can do probabilities.
We have just positive and negative. Where's the probabilities?
I mean, we can say one of them is we just predict how likely it is to.
Well, we're not predicting. We want to learn this bloody thing. We're not predicting anything. We just want to say like how I turn my goat label into positive or negative. I mean, you're getting somewhere. I see your point. I see your point.
So it's just about doing it binary, like.
Yeah, it's a binary classification now. I mean, the classification is like positive or negative. I mean, I didn't say like, oh, let's predict the probability of something. No, I'm saying like, I want to say whether it's positive or negative because this is what we have in the data. We want to model this. 0, 1 is good. Anything else?
When you say 1 minus, then whatever you want.
I don't think you are up to something. Indicator function does absolutely rings a bell, but I don't think this is what I'm asking for. But maybe I'll ask you later. What do you mean? Maybe we'll get to there. So let me just. I mean, we can do like minus 1 and 1. For this would be negative and this would be positive sentiment, or 0, 1. So basically, it's arbitrary. We can do whatever we want, but some of these have some of these are better than others. So if we were doing the standard machine learning with did you hear? So who knows like SVMs, support vector machines? Some. Okay, great. So in SVMs, you're using -1 and 1 because it's convenient for SVM to work. We're not doing subprefectural machines. We're doing logistic regression. So we say, yeah, 0 and 1. It's arbitrarily mapping the category. So we're saying, yeah, I mean, this is up to us to say that 0 is negative and 1 is positive. It could be the other way around. It's up to us to decide and keep it in the head, But 0 and 1, this is good. And we turn the problem like, okay, now we solve this. We know like we can have a number for the meaning of this, positive, negative. This is very easy. But now the tricky part is like, again, this natural language text and the vector here. So how do we represent natural language text? This is the task now we need to solve. Okay. So we need to transform text into a fixed size vector of real numbers because, this is what we need. We need some vector of numbers. Vector of numbers. And what we are having as the input is this. And it's actually one actual example of IMDb, one of my favorite movies ever. You see the typo here. I mean, there's a white space missing. Oh, geez, these people cannot write. Here, and again somewhere, yes. Which will, it might have consequences down the road. Anyways, people on the internet. One of my favorite movies ever, The Shawshank Redemption, is a modern day classic, as it tells the story of two inmates who, actually it's a good movie. I don't know, did you like it? It's kind of cool. And as usual, the book is better. The book is like 7 pieces of Stephen King, like a novel. I mean, it's kind of cool. If you're a fan of Stephen King. I used to be one. Anyways, so this is a text. So we need to turn this into vector. Okay. So we need to start with thinking of what do we have here? We have things. And we touched this already in the first lecture. We start with words. So what is the word? Do we still have the linguist in the room? There was one linguist here. Okay. So now we can leave linguistics alone because I don't care what a word is as long as we can somehow work with that. So words are sequences of letters separated by white space. This is a good definition. You take a sequence of letters, and if there's a white space left and right, you call it a word. I'm glad we don't have the linguist here now, because they would disagree maybe. But it's kind of, that's okay. It will get you far. Okay, so the question is like, well, you remember this comma and whatever. So is dog, question mark, dog dot, and dog the same word or should be different? Okay, so let's do the better. Words separated by white space or punctuation should be word. Okay, this is great. This will get us somewhere. So then this process is called tokenization and splits text into tokens based on white space and punctuation, which works nicely for some languages, such as English. Come on, look at this. White space, white space, white space, white space. Punctuation, white space, white space. Okay, good. So it will basically, chunk the text into tokens, and that's good enough. Sometimes some language, I don't speak any Hebrew or Arabic, but that's what I read in the book. It's like sometimes they don't have white spaces, and I'm almost pretty sure that Chinese has no white spaces at all. So if you are a speaker of any of those languages, written languages, then you will understand the difficulties of saying like, oh yeah, just split the white space and punctuation. And unfortunately, or fortunately, unfortunately, like NLP is very English-centric thing for many various reasons. So most of the papers are actually working on like English corpora. Don't ask me why. Maybe it's the reason why we're actually having this in English as well. There's some there's some reasons in the world. So you need to pay special attention if you're working with other languages. But maybe we have a solution to that. We have a better algorithm than just this. And then what is a token and what is the word? So cat and cat have the same meaning, but is it the same word? Like one is a capital and one is cat. So sometimes people are saying, oh, I'm gonna just undo the capitalization. I'm just lowercase all the words. Maybe it's okay. Maybe it will work. In some cases, it won't. And now here, New York. Okay. So compounds. Is it 2 words or 1 word? It's not compound. It's like multi-word expression. Is it 1 word? Should I treat it as 1 token or 2 tokens? I mean, it makes sense like it should be 1 token because it's like one thing. So, you're running, once you start digging deeper, you're running into all these things like what is a word? So, we will be using the term word or token very loosely. Mostly we'll be talking about tokens, which sometimes they correspond to word, but in reality the story is just more complex than that, okay? Any questions or Any other fine, nice examples from languages that you speak that are even more complicated than Chinese or Arabic? Anybody speaks here Arabic, like, or Chinese? Okay, how is it like the punctuation in written text?
In Arabic,
Mm-hmm.
um,
Not punctuation, sorry, like white spaces.
so in Arabic there is white space
Mhm.
between each word and the other word.
Oh, is it? So this is wrong here in the slides. Yes, I'm sorry, I took it from from a book. How about other languages? Chinese, maybe? No white spaces.
Yeah, I think it's the same problem like New York. Like, how do you count it as a word, one word or two? Because we have like for vocabularies, for example, uh, let's say New York
Yeah.
in Chinese, and like, because every
Is it one character? Is New York one character in Chinese or multiple? Two characters.
So how do you count it as one? If you take only one character, it has its own meaning.
Sure. Okay. So you cannot just chunk it by characters and say like, oh, these are my words. Yeah. Okay. Yeah. So it's very tricky. Yes. I mean, tokenization of Chinese is very tricky. That's what I know from some literature. Good. But anyways, let's assume now we can chunk words into chunk text into words, and then we're gonna build a vocabulary. So our vocabulary is gonna be static, fixed size. So we decide upfront. Let's build a vocabulary by tokenizing maybe some training data, maybe, or some even like external data, which is not for our task. So let's take the internet, and learn the vocabulary from the internet. And typical sizes of the vocabularies are 20,000 to 100,000 words or tokens, words, or could be more, could be even less. These are the typical sizes. And then in this vocabulary, I show something very small, and I think this is a vocabulary of like the most common 3,000 words in English. I took it from the internet, so no guarantees, which are sorted by alphabetically. But they don't have to be sorted alphabetically. Excuse me. It could be any order, whatever. But the only thing is like each of the words has its index in this vector of vocabularies. Okay, so and now we're counting from 1, so it could be like counting 0. So 0 base index or 1 base index, it doesn't matter. So there's a vocabulary. So you have a list of words and each have an index. Sounds good? Sounds easy. Okay. So now, so we have a list of words mapping. So we have a vocabulary which maps words to numbers. 1. So abandon is 2. Cat is 852. Okay. So we have this, and now we come back to this text. So now we can map each word to a number. Yeah, this is good. Can we turn this into a vector of numbers? We can. If we say this is 22, 30, favorite is 800 something, yeah, we can turn this into a vector of numbers. What is the issue here? It won't be a fixed size vector, because why? Yeah.
It depends on the length of our text.
Exactly. Like if you have a longer text, it will be much longer. If you have a shorter text, it will be even much shorter. So that's a bad idea. So no. Maybe something else. How can we turn this into? Yes?
Also, I think a problem about that is that we have exponentially many combinations.
Yeah, I mean, if this is going to be any useful, it's a different story, and the answer is not really, But even like turning this into a vector is tricky. So
I think they're called embeddings. It's like semantic representations of the text.
yeah, we'll get to that.
Okay.
It will be one of the solutions, but how to get there is like it's a different, it's a way of going there. Embeddings is So how can we solve this now? Okay, so yes. Oh, you would say like, oh, let's chunk it in parts and do the vector, and let's chunk this and do the vector. How would you combine these two vectors? Yeah. So you have a fixed vector for one part and fixed vector for the second part, but you need to represent the whole text. So can you combine them together somehow? You can make an overlap, so you would say like, let's plug it here and sum them up. Maybe average. Yeah, it's kind of tricky. But you're onto something actually. You're taking it an interesting way, which will get us to the answer. So what we're gonna do instead is, but you know what? Each word actually has a fixed size vector in our vocabulary. Because if I look at a cat here, cat can be represented as a vector of all zeros, and at position 852, it could be something like that. Right? This will give me a representation of cat in the vocabulary. Basically, the position of cat in the vocabulary will be the 1, and the rest is 0. This is called one-hot encoding. Does it make sense now how to represent a word as a vector? So we can represent now a word as a vector. This is what this vocabulary is giving us. So now, following your argument, it's like we don't chunk the text into pieces of text. We take each word, turn this into this vector of size vocabulary, and stack them all together, and maybe sum them up or take the average. I would just sum them up, or maybe, I don't know, like take the average is like one of these options. You follow? Like, yes, you have a question. Okay, what if the word is not in the vocabulary? We'll get to that, okay? Hold on your question, this is good. Let's assume like we have all the words in the vocabulary. So, and what we end up with is the back of words or average back of words. So, here's a very fancy formula for this stuff which is somehow clear. So let's have a sentence which is a cat said. Very stupid sentence, but this is an example. So we can represent, as I said, each word as a one-hot encoding from the vocabulary. So, what is the A? So this is this vector, because at position 1 in the vocabulary we have A. So 1 at position 1 exactly, and then zeros, until the end. That makes sense? So this is how we represent A. How we represent the cat is, again, we look up in the dictionary, and at position 852 it's 1. So we turn it here 1, and everything else is 0. And then the last word set, the same kind of thing. So position, where is set? Somewhere here, 2000 something, whatever. So we have 3 vectors, 2, 3, and this is 1, somewhere here, somewhere 1, and the rest is just zeros. And what we're gonna do is that sum them together, so it's gonna be 0, 0, 1, something 0, 1, something 0, 1, for 3 words, and divided by 3, and this is gonna get us like the representation of text. The average sort of value of words. The question is like, this sounds stupid, like, will this work? And the answer is yes. You'd be surprised how well this actually, how far will get you, because for some tasks. Because what you're doing here, you're saying, oh, there are some words in my text which, there appear some words in my text. They carry some meaning, and I give them this value, just 1. They appear there. And if I do the average, I'm getting sort of like, oh, if what I'm doing actually here, if I take the average, if I take the average words, I'm turning this into something interesting.
I'm concerned about the order of words, because
That's a good story. So question 1, question 2, order of words and out of vocabulary words. Keep these questions. But let's assume we figure this out later. But what are we getting here? So if we do this average, we're getting like 0, 0, 0.33. This is also 0, 0, 0.33, 0, 0, 0.33. What are we getting here?
we are getting how many times each word appeared in a text.
This is what we're getting here. But here we're getting something more even interesting, yes. Some sort of hotspots, like, okay, some even more, yes?
Normalized distribution.
So we are getting normalized, we're doing normalization, and after normalization we get a probability distribution. Okay, cool. I mean, basically, this is a probability distribution, sort of my document over the vocabulary. It sums up to 1 because it's normalized. And then it's telling me, yeah, you know, this, I mean, is it any helpful to think about this? Maybe. Maybe later for these, what you mentioned, embeddings, sort of. Might be interesting. But this is giving us like sort of the distribution of words in my document. How are the words distributed? So there's maybe the word D will be most likely in there, and there will be some lesser words, and most of them will be 0. So now the question, so does it make sense so far, so good? Except for these 2 questions. So out of vocabulary words is a problem. Let me fix it very easily. I'm gonna add one very special token here, which is called AOV. I'm gonna give it a special index, 3001. And I'm gonna say like, okay, whatever I see which is not here, I'm gonna call it out of vocabulary and give it a special token. I'm bypassing the problem, saying like, these words don't exist, and maybe I don't care. It will work surprisingly well for many cases, but sometimes not. So we have a solution for this. Now your question was the order of words. Yes. Interesting. Yeah. So this is the example, by the way, the cat set. Yes. The order of words. So where does the word order matter? Almost everywhere, right? I mean, the word order actually is great. They give me an example where if you change the word order. Yeah, the movie was very stupid sentence. The movie was good, not bad. You're gonna run into troubles because the movie is not good. Yeah, it's stupid sentence. You get the idea. I mean, I'm pretty sure there are better examples like the word order actually matters for actually even the task. So, of course, if you throw, and that's why it's called the bag of words. You sort of take the words and throw them in the bag, and the ordering of the words don't matter in this average. Like here, the ordering of words doesn't matter because just like everything in bag and sort of like taken into one vector. But for some tasks, actually, it could be very, very helpful. I mean, it's gonna be like a super baseline good representation of text. Okay. Yes. Yes, yeah. The problem we're solving here is how to turn this text into the vector which is plugged here to this function. Other questions? Good. So now we're coming to your question, which I already answered. I actually answered exactly how it is here. So we just adding like unknown or out of OOV or token, which is the unknown word, and sometimes it doesn't matter. In machine translation, this is a question. Okay, so how do you translate a word in machine translation? So from one language to another, if your word is not in the vocabulary, what are you gonna do? You translate it word by word maybe, or token by token, and then you end up with something which is not in the vocabulary. What are you gonna do? You just copy the input to the output. Surprisingly, it will just work most of the times. For names, of course, you don't have all the names in your vocabulary. Like, why? So typically, like the previous generation of machine translation said, unknown words. No, I just copy the input. Sometimes most of the times it works. Good. But the problem is, what is the problem of this one-hot encoding? Yeah.
It's super sparse.
It's super sparse. Okay. Yeah, it is sparse. Is it the problem?
I mean, it's sort of inefficient in that way. It can waste the large text a lot of memory.
I mean, if you have like 50,000 bytes, I wouldn't call it like wasting of memory, to be honest. Could be. Okay, you need to represent it like in something. The other solutions won't be any better. So I'm saying like, this is not the issue. Like, but yeah. If you do neural networks, you have to have a lot of inputs. So? Sorry, did you say it gets very wild or white? White. Could be, but I don't think it's a problem, actually. Could be. Like you have some input vector, could be an image. Like, how big is an image? 3,000 times 3,000 pixels, 10,000 something, whatever, 100,000 pixels maybe.
We're wasting a lot of zeros for.
Yeah, we're wasting a lot of zeros, but it's. I don't think this is the problem actually. The problem is, yes, you're.
We lose meaning because we represent any words with just one, so all the words have the same meaning.
Yeah, so you're up to something. I mean, this will be motivation later on for some of these embeddings, but we're saying like each word is somewhere. I mean, there's no notion of meaning of words. That's what you're saying. Like each word is somewhere in the vocabulary arbitrarily, and it just gets one. But if two words are, cat and kitty, sort of similar words, or Jane and Joe. You get the gist, similar words. I mean, we kind of want them to be somehow similar in the representation, but they're not. They're just distinct kind of things in the vocabulary. So this is the issue we're running into. And also we're running into the issue like, okay, so this out of vocabulary is actually a big issue for many reasons. So we wanna bypass that. So what we are doing, I mean, how can we fix that? Let's look deeper into the words. So we don't split the words by white spaces, but we can split them somewhere in the middle of the word, right? So we're gonna do, for example, this sort of byte pair encoding means, here's an algorithm, and once you see the algorithm, you will understand what it means. So we're gonna basically build a vocabulary not by splitting words by tokens, but by starting by just a single characters. So we're assuming the words have characters, and we start with the characters. So we split the corpus into characters, and this will be our initial vocabulary V. And then we look which pairs of characters are very frequent, so they occur very frequently in the corpus, and it gives us a hint like, oh, they have something in common. So we should maybe treat them as a one token. So we will merge these two things, these two characters together, and add to the vocabulary. And we will repeat over and over until we reach the size of the vocabulary. And if we do it over large corpora with multiple languages, and even like with multiple writing systems, we will end up with everything we need to build the words by the elements of the vocabulary. Because some words will be one token in the vocabulary, some words will be consisting of two tokens in the vocabulary, but we don't have any out of something, because eventually, if the word is not in the vocabulary at all, or the subparts are not in the vocabulary at all, we can reconstruct them just by the letters, because all the letters are in the vocabulary. So let's look into how to build this, like as an example. So we have a very toy corpus. This fat cat with the head is in the cave of the thin bat. It's an example, okay? So now we look what are the most frequent combinations of characters, and by exploration, we found that T and H are so frequent that, like the most frequent. So we're gonna say, okay, you know what? TH, let's add it as a TH, like one token to the vocabulary, and then do it again. So merge them. So basically, we merge TH here and so on. And now we look, okay, what are the two most frequent combinations of two tokens? And this time is going to be AT. So where's AT, 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 and so on, 4 times. So again, we're going to merge them, which means AT as a single token is going to be added to the vocabulary. And again, we merge them, so TH, AT, TH, AT, and so on. And now what's the next? I don't know, something. Maybe actually it's going to be THE is the most frequent one. So yes, exactly. So we're going to merge THE as one single token and add it to the vocabulary. Yes, this was it. Merge into single token and continue and so on. So at the end of this process, the most frequent words will emerge as single tokens, and rare words consist of still unmerged subwords. So the rare words, like here, cave, is still a combination of letters which we all have in the vocabulary, but some common words such as at and D, which are actual words in daily use, will be its own tokens. So this will prevent out the vocabulary, and then we can tokenize each text into these sort of character tokens, and that's it. Does it make sense? Yeah? Any questions? Yes, you have a question.
What if a word would have like two meanings?
Can you hold this question to next lecture? Good. Because this is the same problem as we were discussing, like the meaning of words is lost. Yes, but you have a question? In the vocabulary, yeah. Yes. So yeah, but this is how you construct. So what we are, okay, let's come back like why we are doing this. So here we were saying first, we're tokenized by splitting at white space. And we saw like, now we have words which are not in the vocabulary. But we are basically building the vocabulary. Here the vocabulary consists of actual words. What we did is with subword encoding is that, we learned this vocabulary, but the vocabulary will not be consisting of words as we know, but letters, some very weird combinations of letters. And then if we do it like long over for big text, we will also have the words. This is the idea, but this is just the vocabulary. And we use this vocabulary for representing text, as an input. But this is just one time fixed vocabulary prepared. Okay, first. We might end up with multi-word expressions. We might end up in New York in there, actually. Yes, that's possible. We might end up with New York. You were second.
When do you stop?
This building? When do you stop this process?
Yeah.
I mean, you would say, okay, so max size of the vocabulary is gonna be 50K.
Okay.
And once you reach 50K, you arbitrarily choose like the size of the vocabulary. It's roughly, I think, like 100K is the standard size of byte pair. Yes.
Why are we searching for the most frequent representation of characters? But we cannot just use the basic consisting of.
You can use the basic vocabulary. Exactly. You can use the basic vocabulary, but what is a vocabulary? I mean, what is a vocabulary? Like, how do you start? The idea of this is now, if you run this over different alphabets, you will end up with a single vocabulary having all these Latin characters and words, plus all these Arabic characters and words, plus all the Chinese characters and words, plus all the Burmese characters and words, and the Georgian characters and words, and all the Cyrillic you get the gist. So you have a single vocabulary for representing all languages, or subword units for representing all languages, which will be super beneficial in machine translation.
But you could do this once for every language.
Yeah, you can do it for every language separately. The idea is like if you do it like in multilingual, the benefits will be also you can build multilingual models, because maybe the models will also learn something from all these languages. This is the whole idea of like going from single language and single vocabulary and single model, it will work, no doubts. But you can also benefit from multilinguality and do like multilingual vocabularies in the first place. Yes.
I had a question. So in this particular example of sentiment classification, wouldn't this actually perform worse than the original Backpropagation approach?
Whether subword units will perform worse than the original backwords?
Because, for example, the original one, we had like still the words, so the model could, in essence, learn that if there's lots of these words, that means it's a bad sentiment. But here, if the tokens would be small like that.
Yes. Okay. So I think like there's a little bit of confusion here, because like let me give an example of some other byte pair encoding where you see like it actually will work pretty well for representing text. So another example is sentence piece, and I think this is actually usually used by modern GPT-based models, if I'm not mistaken, which is actually it's splitting the word. So it's basically the same sort of like start with the letters and build up the subword units. But it has a very nice property. It keeps also the white spaces. So you can reconstruct the original text from sentence piece, which is not the case of byte pair encoding where you took this into account somehow, the spaces in between. Here, so here's an example of, sorry, this is byte pair encoding, exactly, because there was, here in byte pair, excuse me, rolling back, so byte pair is what we were discussing before. Here, you kind of assume there's a white space here always. And if there's no white space, there's this very weird characters to merge these words together. So net, Anya, who is one word, and you're splitting this into the subword units, net, Anya, who, and correct, using this. So you're losing the information about the white spaces, which is kind of bad because if you're generating text, you want to know where the white space should appear or not. So white space has to be part of the vocabulary as well because you need to generate the white space. So sentence piece escape the white spaces with this underscore and tokenizes the input into arbitrary subword sequence when you might end up with multiple words as New York, for example. So here's an example of sentence piece. So hello world, which is a bad example, but it shows that the space is actually part of the vocabulary in some of these subword units. So everything is learned from data, including the white spaces between words. That's the idea. But your question, whether the representation is going to be better or worse, well, look at this example here at the top. Let's assume this would be a text. So what you see, it's actually, I think it's a real kind of byte pair encoding text. And you see like there's most of these words are actually there. They are learned because they are just so common. And some words which are not so common in your training data is like Netanyahu, which is kind of split into 3 words. But it won't impact your sentiment classifier maybe. I'm assuming like, I see, like a very weird director's name could be split into something, but it doesn't impact the sentiment of that. So you have one more question and then you.
No, so I was just going to say, so yeah, of course, if after it's done, lots of the words are still there, then
Yeah,
still
exactly.
The question is that if it wasn't lots of words, and we had lots of characters, that would of course.
Yeah, so I mean, you need to build a good vocabulary in the first place. Like if your vocabulary sucks, then you're doomed for your task. Yeah.
How much text do you need for having this representation? Because I mean, you can clearly see the separation between the words, and Netanyahu, for example, is not being classified as one word. So I think you need a lot of data for it.
Yeah, you just take a internet crawl and run the sentence piece tokenizer.
Okay. Isn't that inefficient somewhere?
It takes a day or so. Like the original BPE here from this paper, as far as I remember, from, I don't have the reference, something 2016 sentence piece. No, this is a newer, but even older, 2016-15 paper on Japanese and English. The byte pair encoding, like finding these, this algorithm, it's inefficient, but they did some like crude optimization and they run it for a day on like very large corpus back in the day. So you do it once and then it's good. So you train your tokenizer one time and it's good. Yes.
For the second example,
Yeah.
why do we escape white spaces, but at least in this example, keep the dot as a word? Why not do it in the same way for the white space?
So no, I mean so why? Yeah, so white space is important because it does have a character. Why didn't it learn as a this is interesting. Why do we actually turn white space into something which is not a white space? Because we can keep it as white space in the text and just learn everything. Yes.
Why is the white space not a word like the dot is a word?
Yeah, that's a good question. I don't know. I mean, I think this is the design choice to turning this into. Why wouldn't it picked up, and the dot were picked up first? No, actually, no. I think the reason is like in your vocabulary, you do have like this white space character, you do have the dot character and everything, and you have some words which are like WOR, but you don't have words which is like LD dot. They didn't make it to the vocabulary. So if you have a word like LD dot, there is no such a word in your inventory. So you would need to go to, you might have LD and you have a dot, so you split it into 2.
Yeah, I get that, but why don't we do that for the white space? Why don't we have hello and Ruhr, the same way we have LD and dot separated.
Because in your vocabulary you learned, there was a lot of occurrences of these, like maybe there were some word, WOR, and this white space so many times together that it plugged them together into the vocabulary.
Okay, I get that, but why don't we add the characters? From my understanding, we add characters like the alphabet.
Yes, and the white space and the white space and the dot. We have it, everything in there. And here they were merged together, so they made it into one token.
Because they were the longest token.
Yeah, yeah.
Is there some convention about always keeping the white spaces on the left side?
I think it was just, I have no clue, to be honest. I have no clue. I think it was just picked up like...
Because some, I mean, I'm wondering
no.
maybe it could be possible that then you have like 2 white spaces.
Yeah, so I think the only solution is to look into sentence piece. I mean, you can download it and look into the vocabulary dictionary and see what's in there. I don't know. I haven't done it for a while, so I don't know. Okay, any more questions? 1, 2. Okay, first.
We talk like we always take representation of the least tokens. So
No, you take the largest one. You take the largest one, yes.
When the algorithm is searching for if this word is in our vocabulary, when it knows that I should stop now and go search for this word, because let's say for example.
Oh yeah, okay. How do you tokenize? So you have inventory of words, and you're going by character in your input text. And how do you tokenize it? Just string matching. You just start exploring your vocabulary, and you do string matching here, and you keep paths here. I think there's like very efficient algorithm to do so actually. And once you backtrack your solutions, like which kind of vocabulary items you already matched, and once you're over, then you say, okay, I'm matching this character, this word. So there's some sort of pattern matching, like string matching between the words you have and the options in the vocabulary. How exactly is it implemented? Actually, I never looked into, but it should be some efficient algorithm, some like log-n complexity or something. I guess. But I don't know. It's a good question. I mean, you can look it up. Look in this implementation of sentence piece. You'll find it online. There's the answer. Okay, good. We're absolutely running out of time because my next 32 slides, we won't make it at all. So I think let's keep it for next time because it's why not? And today's exercise, we're gonna do some implementation. So I posted yesterday on Discord. So make sure you have your IDE ready and you can import a project and you can run the first unit test. If you don't do so, you might do it on the spot, but usually people struggle for some reasons to make it work. So make sure you show up with the code running. So see you later.